Okay, guys. So, are we ready to start? Okay. So, welcome to the third lecture on these hands-on activities and tutorials for developing applications for the Internet of Things. First of all, how many of you have an account on Xively now? Nobody, right? One. So, but so you were the only one who tried, or you don't know? Ah, l'anno scorso. So from the last year. Okay. I don't know if it's good or bad, right? It's good. Okay. So let's wait a couple of minutes more while everybody sits down. Okay. So today we are gonna start looking at TinyOS, okay, which is this operating system for developing applications. Now, from now on, what I'll try to do is to show you, the tools that you need to develop application, and we will also look at examples. Okay. So if you bring your laptop to the class and you use the virtual machine, we can try to make the lesson a little bit interactive. Okay, so I will show something and you can follow me in coding so that you can try on your laptop what we are doing actually. Okay, so basically you learn while I teach, which can save a little bit of time. Okay, so of course, if you want to bring your laptop, this is very welcome. And as usual, if you have any problem with the tools, like the virtual machine and this kind of stuff, please tell me, okay? Good, so we start with TinyOS, okay? This operating system for wireless sensor networks and for developing application for the Internet of Things. I will split the topic into two lessons. So today we will look at the basics, so how to write very simple applications, um, how to use the main components of the system, and so on. While next week we will see the simulation part. So once you have an application, how can you simulate it, and how can you understand that everything is working properly. Um, in any case, today we will also see a little bit of simulation, okay? So that you can start playing with these tools also on your own. Okay, this is important since the time that we have for these classes is very limited. So of course I cannot enter into very deep details. And if you are interested, you should try this kind of solutions by your own. Okay, so I will give you the main tools in order to try these applications. Then if you are interested, you can elaborate a little bit on your own. Last thing before we start, regarding the projects, they are almost ready. Okay, so I guess that next week or maybe also before, so 100% for the next class, there will be, let's say, a PDF on the website which describes the projects. Okay, and of course this year we will give, I guess, 3 projects. Okay, one which is more on the network side, so where you have to play a little bit more with sensor network protocol and this kind of stuff. One which is more on the application side on the sensor network. So I will give you a project on developing an application for a body sensor network, where you have sensors that gets measurement from your physical activity basically, and you have to monitor if there's some abnormal behavior or this kind of stuff. And the third project will be something more related to the web. Okay, so I'll try to make the project so that you have to use Xively or Sixth Sense or Node-RED and this kind of tools for the web. Okay, so most of the effort will be on the application side from the client perspective. Okay. Of course, if you have an idea or if you want to develop a particular project which is not contained in this list, this is very welcome again. So you can send me an email explaining the kind of project that you want to do. Okay, it can involve both software or hardware. In case of this latter, so in case of hardware, we will not provide any hardware this year. Okay. So if you have something already, like if you own an Arduino or some other platform and you want to develop an IoT project for that, this is welcome, okay? The only thing is that you have to, let's say, contract with me this project, okay? In order that you at least, so I can give you the full 8 points, let's say, okay? So the project must be enough for me, okay?
If you have already started working on something that is related on your own before you started, does it count?
Yeah, of course it may count, but you have to tell me first. So you have to send me an email explaining what are you going to doing or going to do, and I may ask you for something more, you know. Okay, so depending on what you want to do. Yeah. So the guidelines for project delivery, I guess they are on the website. So it should be, so the project should be 8 points if you deliver it before, I guess, the first appello. Could it be? 1st September. Okay. So if you deliver it before September, you get the full 8 points. After September, you get maximum 4 points. Okay. So that is, you have plenty of time. You have till September. So, okay. Very good. Other questions? No? Okay, so let's start. So as I was saying, we will split this topic into two. Today we will see, let's say, the first points here. So how to, build a very simple application, and we will see some examples again. I have also with me some hardware, so I can show you how, typically building and deploying application is done. It's very, very simple. And we will also use a simulator, okay? So that even if you do not have the hardware, you can still run it and see if it's working or not. So we will look at basically two types of applications. One which is just a very, very simple starting point, and it's called the Blink application. So it basically, its purpose is to introduce you to the main components of the system, okay? And then we will see an application which actually uses radio communication, so exchange of messages and so on, which is a little bit more interesting because it's basically the basis for any application of the Internet of Things. Then the next time we will see how to simulate a little bit in details an application, so how to set up a network topology, set up the links, decide a radio environment, and all this kind of stuff. Very good. So let's say if you want to go into the details of TinyOS, there's a very, very nice programming guide at this link, okay, which contains, let's say, examples, guidelines, and everything you need in order to start by your own with TinyOS. So if you have any question, refer to that guide. One of the, let's say, main features of TinyOS is that it is very, very well documented also online. Okay, so for any problem that you have, probably just a Google search is enough to solve your issue. Okay. So we will start by looking at the main components. If you remember from the first lesson, we partially already looked a little bit at that. So we will see how to basically wire together components, how to call particular actions on the components, these are called commands, and how to manage events which are coming from the components. Okay. We may also look at a little bit at tasks and what is their, let's say, purpose. Maybe not today, but in the next lesson. First of all, let's just recap the main limitations of TinyOS. Okay, we are working with sensor networks, so we have constraints in terms of memory, processing, energy, and this kind of stuff. This translates in the operating system in basically three constraints. Or let's start with all these constraints. The first constraint is that you do not have dynamic memory. Okay, so all the memory that you need must be allocated, and so you have to know exactly what is the memory space that you're going to use. Okay, meaning that all the variables that you need, all the arrays that you potentially need, must be declared at compile time. Okay, they cannot be dynamically allocated. You also have some constraints in terms of variables that you can use. Okay, you cannot use let's say floating point variables. Okay, or at least you can use them, but you have no hardware support for floating point operations. Okay, so you have to be very, very careful when you do floating point operations. Okay, and of course, also since your processing power is limited, you have constraints on the type of operation that you want to do. Okay, so very, very intensive operation like Fourier transforms or other type of complex operation are not allowed, or better, they are allowed, but they take a lot of time, okay, to be executed. So you may not want to implement them on the sensor. And then there are other, let's say, details that we will learn while we look at the code. In order to write an application, and we will see this in a couple of slides, well, it's actually very simple, because we just glue together components which are already provided by the operating system, and if needed, we declare additional components, okay, which basically do the functionalities that we want to implement. Now, the main, let's say, items in TinyOS, if you remember, we have different items that build the system. Let's say, I would start with this. The list of actions that you can call on a component are contained in those interface files. Okay, so an interface file is something that lists all the actions, so all the commands and all the events that a component can use. Okay, now just to give you a more, let's say, direct example, there's in the documentation of TinyOS on the web, for example, here, this is for the Telos B platform, which is this one. You have all the interfaces that you can call here, that you can use. Okay, so for example, let's take one which is understandable easily. For example, the timer. Okay, the timer interface. So this is an interface, and it just lists all the commands and all the events that a component can use. So for example, if you use the interface timer, you have this sort of commands, okay, that you can call. For example, get now, which is a function that returns you the current timestamp, or start one shot, which schedules a timer for being fired in the future at a particular time in the future. And you have only one event, which is the events fired here, which basically is an event which is signaled by the operating system when the timer expires. Okay, so you can imagine that if we use this interface and we connect it to a component, we can schedule a time in the future to get an event. Okay, this is very useful for all those systems which are scheduled in time. For example, if you need to take a measurement every 10 seconds, what you do is you set a timer for being fired in 10 seconds, and when the timer fires, you get the measurement. Okay, and then you schedule a timer again. Right? We will see this. So here you have all the interfaces. And as you can see, there's no, let's say, source code in these interfaces, okay? It's just a list of basically functions that you can call. Let's switch back here. Then we have modules and configuration files, okay? Now, the modules are, I would say, the most important files in TinyOS, and they contains the implementation of a particular interface. Okay, so modules contain the source code which is executed, okay, when you call a certain commands or when an event is triggered. Okay, so the modules contains actually the operation that you need to perform. Then we have headers file, which are just header files, plain headers files like in C, so they declare, for example, constants or other variables that you may need. And then we have configuration files, which basically wire together different components in order to form an application. Okay, we will see an example now in order to understand what's happening. Let's start with this Blink application. Okay, the Blink application is basically the starting point for I would say any operating system for sensor networks. It's an application which just boots up the system, okay, so loads what you need, and then keeps 3 timers, one at 1 Hz, one at 2 Hz, and one at 4 Hz, and whenever each one of these timers expires, a LED is toggled. Okay, this kind of hardware usually have 3 LEDs of different colors, one which is red, one which is green, and one which is yellow or blue, depending on the model. So what we are going to do is to connect each timer with each LED here, and basically we are turning the LED on and off depending on the timers. Okay. So if you have the virtual machine which is running, we can all together go directly there and see the source code of TinyOS, okay? So that it will be very, very easy to understand. So the applications of TinyOS are in your home folder, in the TinyOS main directory, then in apps, and here you have some examples applications that we will use throughout this course. We will go into the Blink folder, okay? So let's just do a little trick here. Don't worry about this, just for a moment. Okay. So this is the Blink application. It's basically, it contains 3 files basically. One which is the configuration file, one which is the module, okay, and then a make file which contains the instruction for building the application. Okay, let's see the module first. Okay, so let's just open the file with gedit, and maybe we can also highlight the source code. So this is the implementation of the module. Okay, well, it includes this header file just for using timers, and then we have first initial declaration part. Well, we basically declare which are the interfaces that we are going to use in this application. Okay, so as you can see, we are using 3 timers: timer 0, timer 1, and timer 2. The interface is actually a timer interface which uses milliseconds as timestamps. And I'm calling these 3 interfaces with 3 different names: timer 0, timer 1, and timer 2, by using the as keywords. Okay, this is just a keyword that you can use in order to name interfaces. Then I'm using the LEDs interface here, which, as you can imagine, it will contain the functions for turning on and off the LEDs. And I use the boot interface. Now, the boot interface is, I would say, the fundamental interface, because its purpose is to boot the system. Okay, so every application that you implement in TinyOS must contain the boot interface. Okay, because otherwise you have no starting point for the application. So after the initial part where you declare what are the components that your application will use, you have to basically give the source code for this application. So actually declare how these components should behave together. So you start another part which is called implementation, which actually please, if you want, excuse me, if you want to talk, you can go outside, right? Okay. So you have the implementation. If you have any question, of course, raise your hand, but don't talk, because otherwise it's a mess. So, by the way, it's funny because everything will go on YouTube, so you know, all these interruptions are blocking the flow, you know. So the implementation part is where you actually declare the source code of events, okay? And as I was saying, the starting point is this part here. So it's the boot.boot event, okay? This is an event which is triggered from the operating system, okay? So basically what happens is that when you deploy your application, TinyOS, the operating system, loads, and when it's ready, it will trigger this event here, okay? So this is your starting point. And the first instruction here is the first instruction that will be executed. So what are we doing here? We are basically using the keywords call, which is used always for calling commands, okay? So for executing actions on a component. And what we are doing here, as you can imagine, we are starting periodic timers on the 3 different timers. We are using different, let's say, periodicities. The first timer is triggered every 250 milliseconds, so it's basically the 4 Hz timer. The second one is the 2 Hz timer, and the third one is the 1 Hz timer, okay? So these timers will fire at different frequencies, okay? Here. So I won't enter into the details of this bus, but you can specify what is the, let's say, time granularity of your timer. And with these keywords milli, you are specifying that these are milliseconds. Okay, so after we have called these 3 events, what we are expecting is to have an event coming back from each of these timer whenever it fires, right? we have scheduled these timers in the future, and now we have to manage somehow this event when they fire. And as you can imagine, here I have 3 events, sorry, here, 1 per timer, okay? And what is happening here is that I will execute this code whenever these timers fire, basically. Very, very easy. So when the first timer fire, I will toggle the first LED. To toggle means if it's on, I will turn it off, and vice versa. Okay. When the first timer fires, I will toggle the second LED, and when the third timer fires, I will toggle the third LED. Okay. So what I will see basically is 3 LEDs that toggle with different frequencies, right? Is this clear? It's very simple, right? It seems very simple, okay? So this is for the implementation, okay? Now let's see the configuration. Oops. So the configuration is contained in the Blink app.c file, okay? Let me just highlight it so that okay. So the configuration basically wires together existing components with the interfaces that I have declared in my module. Okay. So basically in your module you say, I will use these interfaces. Okay. But we have seen that an interface is just a list of functions. Okay. It doesn't contain the source code, right? So at a certain point you have to connect this interface with a component that actually does something, okay? For example, the LEDs interface just contains the function for let's say the name of the function for turning on and off the LEDs. It doesn't contain the actual source code for going into the hardware and turning off the LED, okay? How do we actually do this? Well, we use the components, so modules basically, which are already implemented in the TinyOS system, okay? And so we declare here which are the components that we are going to use. For example, in case of the LEDs is the LEDs C component, and we perform what is called a wiring, okay? So we connect the interface LEDs in our application with the component of the operating system, okay? By doing this, we are basically saying that whenever we call a command on the LEDs interface, we are executing the action which are contained in the LEDs component of the operating system, okay? Now, can you imagine what is the power of this method of connecting interfaces with components? So why, in your opinion, we have such a system? Exactly. So you can build an application. For example, imagine an application that senses temperature, okay? So it will use, for example, an interface which just reads, okay? And it will use a component of the operating system that connects to this interface, and the actual component implements this temperature reading. Now you want to change the sensor, you want to use, I don't know, a pressure sensor, but you don't want to change your application. So you will use the same interface, you will just connect the read interface not to the temperature component but to the pressure component. Okay? So you can remove components, but the interface remains the same. Okay? This is actually useful because you do not have to modify your application, you just exchange a component and to perform a different action. Okay? So that's why we have all these interfaces and components wiring. The main C component, which is here, is the one which provides the boot interface, okay? So the main C component, as you can imagine, is the one that does all the booting of the operating system, okay? And when it's done, it will trigger this event, so that we know we may start. Any other question on this configuration file? You will see while you play with it that it's, if maybe at the beginning can be a little bit tricky because you're not maybe used to this kind of programming. At the end, it's quite simple. Also, this is very important if you think about how we are basically dealing with resource constraints, okay? If you remember, a good operating system for the IoT must save as much as possible, okay? And in fact, what we are doing here, we are declaring what are the components that we want to use so that we do not load useless stuff, basically, okay? So this application just uses these components, and we will load in our application only the components that we need. So we are not, let's say, wasting memory, we are not wasting energy for loading and executing parts of code which are not of our interest, okay? Right? Very good. Now, let me just see on the slides. So this is basically explains what we have done. Now let's try to run it, okay, and see what happens. Yes? Okay, good question. We will see this in the next class, and basically whenever you look at, you see this kind of statements here, these are debug statements and are used during simulation to check that everything is going okay, okay. We will not see them now. We will see them in the next class when we see actually what's happening and so on and so forth. So when you want to compile an application, you have basically the compile process takes these source files and produces an executable file which is which can be loaded on the hardware, okay? Now, the important thing is that you have to specify a make file, and in the make file you have to specify what is the basic application that you will run, and these have to have the name of the configuration file, so the one that does the wiring, and then it has to include the TinyOS make rules. So it's actually a very, very simple file where you basically state what you want to compile. The actual compilation process can be done in the terminal, so this maybe you can do it with me. So if you go on this directory and you type make, and then you have to specify for which hardware you want to compile this application. For example, we are going to compile the application for this kind of hardware, which is the TinyOS B. Can you read? Okay. Do you want me to enlarge the font or not? Yes or not? No, it's okay. Good. So you type make TinyOS B and you run it. Okay. So this compilation process will execute, and if everything is okay, you will end up with these lines here. Okay. Now these lines are actually quite important because they say, first of all, if there are some errors in your code, okay, so that you can check if you have done something wrong. And second, because they will say what is the amount of memory which is used by this application, okay? And you have basically two entries here. One which is the memory used for storing the source code, okay? So in the read-only memory, basically. This is the, the memory which is used to store instruction to be run. And the second line is the RAM memory. So basically the memory used by the variables in your program, okay? This is very, very important because if you remember, this kind of hardware here has very limited memory, like 8 kilobytes, okay, for RAM memory. For ROM memory, we are in the range of 50 to 100 of kilobytes, okay, so a little bit more. Now, the problem is that if you notice that the RAM memory value here exceeds the RAM memory which is available on your hardware, you will have problem at runtime for sure, okay? Because you are using more memory than that is available on this hardware. So you will have, strange behavior and errors, basically, okay? So you also, if you program an application in TinyOS for this kind of sensor, you also have to look at how many bytes of RAM you are using, okay? No, unless you want to, solder actually components on it. But yeah, I don't know how to do it actually. So it may be possible in principle. You just replace the chip, right? But who knows? So I would say no for human being. Okay, so we have now our program which is compiled. Now, what I would like to show you is how to deploy it on an actual hardware, okay? Of course, you cannot do this because you don't have the hardware, but just for looking at it. So I attach my, I attach my sensor to the PC, then I have to specify here that I want to connect the device to the virtual machine, like this. Okay, then let me just do this simple stuff here. Okay, in order to upload the code on this hardware, I type make telosb install, which is the keyword for saying that I want to install it on the hardware, and then I have to pass the USB port on which it is attached. So it will compile the application, then it will basically erase the memory on this device and loading the application that I have compiled here, okay? And as you can see now, I have the LEDs that are blinking at different frequencies, okay? So the hardware is actually following what I have written in the code, okay? Now, this is a problem because you guys do not have this kind of hardware. So how can you see that your code is working or not? And that's why simulation tools are useful, okay? So let me go back to the slides. Full screen. So that's why simulation are useful. So we need a simulator for wireless sensor network, not only because you can try the application without having hardware, so without owning a hardware, but for other reasons as well. So first of all, typically deployments for wireless sensor networks are composed by a large number of nodes. Okay, we're talking about maybe hundreds of thousands of nodes. Okay, that means that in the actual the deployment you will have a large number of nodes that runs the source code. Now, if you decide to write the application, deploy it on this very large number of nodes, and then looking at the behavior, you understand that it's a very complicated task, okay? Because it's so difficult to see whether it's going okay or not, okay? And most likely it will not work the first time. Typically, also, these deployments are located in inaccessible places, okay? I don't know, a volcano, a forest where you want to monitor the temperature, or doing some kind of, for example, fire monitoring. They are embedded on bridges, okay, to monitor the vibrations and this kind of stuff. So it's difficult to actually go there and see if they work or not. So typically what you would like to do is to deploy your sensor network once you are 100% sure that the application is working correctly, right? And of course, it may be very costly to go there, make some changes, and redeploy the sensor networks again. Okay, so you want to simulate first, check that everything is correct, that everything works as you are expecting it to work, and then you deploy and forget it. Okay. So in TinyOS, we have a simulator which is called TOSSIM, which stands for TinyOS Simulator, and this is actually the official simulator for TinyOS, and we'll see it during the next lesson. We will see it into detail, so how to use it, how to set up a very big network, how to set up the links between nodes in the network, how to read the output from each node, how to interface the sensor network with a program which is running on the PC, and all this kind of stuff. So since we do not have time today, what we will do today is to look at another simulator for wireless sensor network. Okay, we will look at the Kuja simulator, which is not the TinyOS official simulator, but hopefully, luckily, it may run TinyOS applications as well. Okay, so the idea is to use it in order to run TinyOS application, even if it's meant to be used for Contiki application. Contiki is another operating system for wireless sensor network that we'll see after TinyOS, basically. So we will very, let's say, quickly look at Kuja now and how we can run TinyOS application into Kuja. So we can do this together, of course. What we have to do is to compile the Blink application for TinyOS. We have already done it. Then we have to open Kuja and create a new simulation. So let's go on the virtual machine. You have the simulator Kuja here on the desktop. You can open it. Takes a while. Okay, so it starts with an empty window, and you can start a new simulation by clicking on File, New Simulation. Okay. You can set up the name of your simulation, and here you have some parameters that we will see later. Okay, so just click on Create now. Okay, so now a couple of windows appear here. You have on the left hand side the network topology. Basically now it's empty. We will see in a minute how to add nodes or modes to the simulation. Then you have the simulation control, so how to start the simulation, stop the simulation, change the speed of the simulation, and then some other windows that we will see maybe later. Now let's focus on the network window here. and let's add a mode, okay? You know, mode is the word for node in sensor network. So you go on modes, and then you go on add modes, create new mode type, and Kuja, this is a nice feature. It supports several different hardware, okay? So you can simulate different hardware here, including the Telos B. Now, the Telos B is also known with a different name, which is T-Mode Sky, okay? It's a different name, but it's the same hardware, basically. So we will create a new mode type, Sky mode, okay? Which basically is the Telos B mode. So if you click on it, another window will appear, and well, you can add the description if you want, and then you have to specify which is the label here says Contiki process or firmware. Basically here you have to deploy a compiled application which can be run on this kind of hardware, okay? Of course, this is the Contiki simulator, so it says Contiki process. But luckily, we can also use it to run a TinyOS application. So we browse our file system. We go to home, user, TinyOS main, apps, Blink, which is the Blink application for TinyOS that we have compiled. We go into the build directory, which is the one that contains the executable. There's another directory, TilosB. And we use the main.x file, which is the compiled TinyOS application. Okay? So we select it. And we can create now a mode. Okay? If you click on create, the simulator will tell you how many modes you want to add to your simulation. We will just add one. And you can also decide where to put them in the network topology, okay? We can use a random positioning, meaning that it will be put somewhere, okay, in the space. Click on add modes, and a mode will appear here, okay? This is mode number 1. Now, if you click on the mode with the right button of your mouse, you have a menu here with some tools that you can enable, and again we will see them. Now we are interested on looking at the LEDs of the mode, okay? Remember, we are going to expect this behavior of LEDs which are blinking, right? The source code is the same. So show LED, this kind of window will appear with 3 LEDs, okay? At this point, I may start the simulation. First of all, let's just set a limit. Let's put 100%. This basically sets the speed of your simulation to be coherent to the timers that you have in your application, okay? So if you put 100%, 1000 milliseconds in TinyOS will be equal to 1000 milliseconds on your PC. If you set no speed limit, well, most certainly your simulation here will run faster than the one that you have in TinyOS, okay? So this can be used to slow down or speed up your simulation. So let's use 100% so that time is equal both in the simulation and in the application. So let's put 100% and then let's click on start. Okay? Okay, so rendering is quite bad on my PC probably because I have the QuickTime which is recording the video for YouTube, so it uses a lot of CPU. Anyway, you are seeing on this LED interface the same behavior that you are seeing on this hardware, okay? So that's how we can simulate and look that everything is going okay. Of course, you can pause here the simulation, you can also save the simulation, you know, in order to reload it and this kind of stuff. Very good. Any question on this part?
I noticed the speed going above 100%.
Yes.
That you said speed, can you specify the speed?
So you can speed up the simulation, okay? So you can make it 2 times faster than the actual speed, or 10 times faster than the actual speed.
Yeah, but we selected 100%, but when it was running, it was going above 100%.
Ah, okay, okay, that may be, yeah, a little bug probably, okay. On my PC it seems to be okay, okay. The blue lights is basically blinking at 1 Hertz, more or less, okay. So it may be something in the PC. Okay. Any other question? No? Okay. Let's move on. Oops. Okay. Let me enter this in full screen. So now you know how to build a very, very simple TinyOS application, how to compile it, and how to run it in the Contiki simulator and see what's happening. Now let's move to the second part. So let's add a little bit of complexity to our applications, okay? And in this case, we will use the radio. So we will start sending messages, receiving messages, okay? So the main component that is used in TinyOS for sending messages is the active message interface, or the active message component. Now this is quite interesting because it gives you basically all the tools in order to send, receive, modify the messages, to write the fields inside the messages payloads, okay, and also to change, for example, the transmission parameters such as the power to transmit your message, this kind of stuff. So it's a very, very powerful component, and basically it's used in all the applications for wireless sensor networks. Now it works, it's a little bit, let's say, deep, so we will look at the main functionalities, okay, and we won't go into all the details that you have. Then if you are interested, of course, you can refer both to the programming guide or to the website documentation in order to understand all the functionalities that you can use. Now, when we use active message, it's a little bit like TCP, okay, where you have to specify on which port you want the communication to be performed, okay. So active message supports what is called an event handler, which is the active message ID, and each time we send or receive a message, we can specify on which ID to send or listen, okay? Something like on which port we want to send or listen. And of course, we have to, so by doing this way, we can also, on one hand, we can send different messages, for example, on different IDs, but we have to make sure that who is sending and who is receiving are actually using the same ID. Otherwise, no communication will be performed. Now, for the transmission process, it will be very easy. Actually, what we will do is, in the configuration file, we will specify what kind of ID we will use. Then we will use a particular command for sending a message, and an event will come back from the component when the message is transmitted, okay? So this is known as split phase interface or split phase paradigm. So it's different, it's more or less like the timer, you know, you call a timer to be fired, and then you wait an event when the timer fires. And it's the same for messages. You schedule the transmission of a message, so you basically call a command for sending a message, and then you wait for the message to be sent. Okay? So we will get a completion signal when the operating system have sent the message. When we want to receive something, as you can imagine, we have a particular event that will signal the reception of a message. So we will implement all our logic to dealing with messages in this event. Okay? So the general idea is the following. So you have a message, you fill the message with something. It could be values that you have sensed from the environment, it could be commands that you want to send remotely for doing something. You specify what is the destination of the message. It could be a broadcast message, or it could be also a unicast message, so with a particular destination. You pass the message to the OS by calling a particular command, and then you wait for a feedback. Okay? On the receiver side, it's the operating system that will notify you when a message is received. So it will signal an event and will pass you a pointer to this message, okay, so that you can go inside and read the fields of the message. Now, probably you know this from the lecture, so have you seen, for example, the 8.2.15.4 frame, right? So you know basically that you have a header with fields inside, source address, destination address, PAN ID, and all this kind of stuff. Then you have the payload, so where you actually put your data. And at the end of the message, you typically have a footer, what is called a footer, which contains, for example, the CRC code in order to check that the message was transmitted correctly and this kind of stuff. Okay? So the same structure, you have the same structure in TinyOS as well. Okay? The only part which is interesting is that header, footer, and metadata, which are, let's say, the parts which do not contain user data, okay, but contains protocol data, are actually implemented by the particular hardware that you are using. So on this kind of hardware, we have the CC2420 radio chip, and TinyOS have specific components for that. But this is a black box for us, okay? We don't have to worry about how to going inside the frame and specify the single bits, okay, to use. It will be very, very easy to fill a message, to specify the destination and send it. Of course, what we have to care about is the data part, so what we want to transmit, okay? So the actual values or fields that we want to transmit is up to us. Let's skip this. So we have interfaces to control communication between two modes in TinyOS, and these are basically the most famous one. We have the active message packet, or the packet interface, to manipulate packets, so to, for example, change the source address, destination address, and this kind of stuff. We have the send and the AM sends for transmission packets, so these two interfaces basically provide the command for transmission and the events that are notified when the transmission is completed. And the receive interface, which basically gives us the events for getting messages from the radio. Let's skip this. The only interesting part is that when we decide to use something which is active message based, so AM, we have to specify on which ID the active message will work, okay? A little bit similar to TCP ports here. Again, let's go directly to look at an example, okay, so that this will be a little bit clearer. And we use an example from TinyOS, which is the radio count to LEDs application. Okay, so we will use part of the component that we have already seen in the Blink application. And in particular, we will use timers and LEDs. But instead of controlling these LEDs with a timer, we will basically transmit, so broadcast a packet on the radio which contains a number, okay? And this number is incremented each time a timer fires, okay? So my application is like this. I have a timer which fires every, I don't know, 1 second. And each time the timer fires, a counter is incremented, okay? So 1, 2, 3, 4, and so on. The value of the counter is transmitted on the radio, and who receives this message will display on the LEDs, on the 3 LEDs, the value of the counter, okay? Now, how do I display a value on a LED? Well, basically, we will convert the value into binary, okay? So a sequence of zeros and 1. And we will use 0 for turning off the LEDs and 1 for turning on the LEDs, okay? So we will convert the number into 3 bits representation. So it's modulo 8, basically. And then we will turn on or off the LEDs according to the code of these 3 bits, okay? So when I transmit the number 0, which in binary is 000, all the LEDs will be turned off. When I transmit the number 3, which is 011 in binary, only the second and the third LED will be turned on, okay? Do you understand this? Okay. So we will go directly into the source code, have a look at the source code, then we will compile the application, and I will ask you, well, actually we will see in the simulator how it behaves. We will see it first on these 2 nodes and then on the simulator, okay? So we can go back to, yes, to TinyOS here. Let's open, instead of the Blink application, the radio count to LEDs application, okay? There are a bunch of files here. There's also a Java message, don't worry about this, we will see it later. Let's look, this time we also have an header file, okay? Let's look at the header file first, because it's important this time. So the header file contains basically constant values that we want to use in our application. And here we basically have 2 constants. The first one, which actually comes last here, is the active message ID that we are going to use, okay? So this kind of code that acts as a TCP port. And in this case, I have chosen number 6, okay? So we will communicate over AM channel 6, okay? So both the transmitter and the receiver should use this kind of number here for active messages. Then we have a structure here which basically defines the payload of the messages that will be transmitted in the network, okay? So this is the only thing that you have to specify, okay? So as I have said, the header of your packet and the footer of your packet are already implemented. You don't have to carry about them, okay? But the format of the data that you have to transmit, it's up to you, okay? So in this case, we will use a payload for our message which just contains a 2 bytes variable, so a 16 bits unsigned variable. Okay, so it means that it's a variable which has 16 bits and it has to be interpreted as an unsigned int, so a number which goes from 0 up to 65,000 and something. Okay, very good question. NX is something that you put before variable types that have to be transmitted on the network. Okay, so in the source code we will just use variables without NX at the beginning, but whenever we specify formats for variables that have to be transmitted on the network, we have to specify NX. This has to basically to do with the endianness of systems. You know what endianness is? How many of you knows? 1, 2, 3, 4, 5. But basically, the endianness of a stream of bits, let's say, is where you put the most significant bit and where you put the last significant bit. Okay? So depending on where you put it on the right hand side or on the left hand side, this determines the endianness of the system. And as you can imagine, this changes a lot the value of the variable that you are reading, depending on which part you're in the variable. So by putting NX here, you're basically forcing all the messages that goes through the network to use the same endianness, so that if they are received from different hardwares which use different endianness, they are interpreted as the same value. Okay.
How the receiver know that should wait for some message to put that command?
Not here. This is just the header file. Okay. This just specifies what is the format of the message. Okay. So if you need, for example, to transmit a message with 10 values inside, instead of having just one variable here, you will have an array of variables. Okay, this just specifies the payload of the message. Okay, now let's open the actual application, which is this one. Okay, this time we include the timer as before, and also the radio counts to LEDs header file, which contains this payload format. Now, first part, which is the declarative part, where I declare what interfaces I will use in my application. Okay, so I will use, of course, the boot interface, which is the starting point. I will use the LEDs interface because I want to turn on or off the LEDs whenever I receive a message. I will use the receive interface because I want to receive messages. And then I will use a timer, just as before, in order to increment this counter and transmit a message on the network whenever the counter is incremented. Then I have two interfaces for transmission. One is AM send and the other one packet, which is used to modify the fields of a packet. And then I have an interface, which is the interface split control, which is used to turn the radio on or off. Okay, this is very, very important because the radio chip is the component on this kind of hardware which consumes the most amount of energy. Okay, so if your application is synchronous, meaning that you exactly know when to transmit a message and when to receive a message, there's no need to have the radio on when you do not expect anything on the radio, right? So you can turn the radio on or off at your will in order to save energy. Okay, and in order to do this, you typically use the split control component. Okay, which allows you to turn on or off a component. Now let's go into the implementation, which is the most interesting part. So first of all, we see a variable declaration, okay? A variable packet of type message t. Now, message t is the type of TinyOS messages, okay? So whenever you have to send a message, you have to use a variable of type message t. Then we have a Boolean variable, which we will use to check that we can indeed send something on the radio. Okay, it basically a traffic lights that will be turned on red when we are sending messages and will be turned on green when the radio is available for sending another message, so that we do not overload the radio interface with multiple transmissions. And then I have my counter, okay, which will be incremented each time the timer fires. As you remember, the starting point of the application is the boot.boot method, which is called when the operating system finishes to boot all the modules needed. And this time, what I will do as a first operation is to turn on the radio, okay? So I will call amcontrol.start, okay? This will turn on the radio. Again, this is what is called a split phase interface. That means that you call a command and then you wait for the command to be executed. When the command is executed, a particular event will come back from the operating system telling you on the success or not of the operation. And in this case, the event is the start done event, which you see here. The start done event comes with an error code, basically, which you can check. Now, if the error code is success, it means that the radio was turned on successfully, so we can start sending messages. Otherwise, I will try to start again the radio, okay? Now, if the radio was turned on successfully, I will start a timer with a periodicity of 250 milliseconds. Okay, so 4 Hz again. Now, whenever you use an interface, you have to provide the implementation for all the events that this interface may fire, okay? In this case, the split control interface here, split control interface, which we called AM control, has just two events. One is the start done and the other one is the stop done. Now, we are never stopping the radio in this example application, so we will never actually receive the stop done events. So we will put nothing inside the block that specify what action we should take when this event is triggered. However, if we do not specify this event, the compiler will complain, okay? It will tell us, look, you are using an interface which may potentially trigger an event which you do not have managed, okay? So that's why we have to specify this here, even if we do nothing, okay? Is this clear? Very good. Now, let's see what happens when the timer fires, okay? So, if you remember from the description, what I want to do is to increment a timer and transmit a message on the radio in broadcast so that everyone that listens can accept it with the value of this counter inside, okay? So, whenever the timer fires, first thing that I do is to increment the counter value. Okay. Then I check the Boolean variable locked. Okay. If the variable is locked, I will return, so I will do nothing. So this is as a traffic light, a semaphore. Okay. If the traffic light is red, I will do nothing. Otherwise, if the traffic light is green, meaning that I can indeed transmit something, I will call the get payload command, passing the packet variable and giving this particular keyword, sites off radio count message. If you remember the radio count message here, is the one that I specified in the header file here, radio count message T. Now, basically, this instruction here gives you a pointer to the area of memory where the payloads of your message begin, okay, so that you can access to that structure and change the fields according. Okay, so it's basically a template operation that you will always use in order to modify the value of the fields inside your payload. Of course, we check if this operation went well, so if the pointer actually contains something. If it contains something, then I will write the value of the counter in the counter field of my payload. Okay, look at the structure has a field which is called counter, so I can access this structure here, and I can override its value with my counter here. Okay, so by doing this, I have prepared a message which contains the value of the counter, and now what I have to do is to transmit the message, okay, to send a message. So what I will do, I will call the send command, specifying the address, and in this case is the broadcast address, okay, meaning that everybody who is listening to it can accept it. I will transmit, I have to specify what variable I want to transmit, in this case is the packet variable, and of course I have also to specify how many bytes I want to transmit, so the size of my message. I will also directly check if this operation is okay, so to check if the error code is success. If it's okay, I will lock the traffic light, okay? So I send a message and I put the traffic light to red in order that if another timer fires and the variable is still red, I will not send another message. Now, when I free this, is on the send done event. So when the transmission has completed, I will put the traffic light to green, okay, so that I can again transmit. Okay, this is something that is used in order to prevent concurrent transmission of multiple messages. So this is for the transmission side. Now, on the receive side, I have a particular event, which is the receive.receive event, which actually gives me the payload of the message which is received. Okay? So what I can do is to check, basically, if the message that I have received has the same size of the radio count message. Okay? So if this condition is true, then what I will do is to read the payload of my message, received message, read the counter value, and then these bitwise AND operation are meant to select the particular bit in order to turn on or off the particular LED on the interface. Okay, so this basically selects the first bit, this the second bit, and this the third bit. Okay. So if I receive a message, I will display the value that I have received on the 3 LEDs accordingly. Okay? I won't enter, of course, into the details of this. It's quite tricky and easy. If you look at it and you run it, you will understand it. It's very, very easy. Right. So as you can see, this application has methods for sending messages, and messages will be sent each time you transmit, the timer fires. And then there's an event that will toggle the LED's value whenever you receive a message. So let's try it on the hardware. I will go into the terminal. Let's open a tab here. Let's go to TinyOS, radio count let's compile it, make telosp, and then let's install it, make telosp install on the USB. So I need 2 nodes, okay, for doing this. The first one is already loaded with this kind of application. Okay, now as you can see, if I have only 1 node, it does nothing, okay? Or at least it's doing something, but we do not see anything on the LEDs. What this node is doing basically is it's transmitting messages, okay? But there's nobody listening to it, okay? Or nobody transmitting other messages so that it can receive a message and display the value here on the LED. Now, what happens if I power on this node? So I put some batteries in. You see, they start blinking. Okay. So this is actually what's happening. So they are transmitting messages and basically displaying the value of the counter which is transmitted. Now, if I remove the power here, this will stay with the last value received on the counter, okay? Right? This one is still transmitting messages, but it's not receiving any message, so it will stay with the last value on the LEDs. I power it up again, and there you go, okay? So this basically shows very, very simple communication between 2 nodes. Now, how can you run it? Well, we will use Kuja, right? So we will run this application into the simulator. This time, of course, we need 2 modes, okay? Yes? In this case, you mean they are fixed? Because I have powered off this other node, so this one is off. It's not sending messages. Since we have programmed the application such that we change the value of the LEDs only when we receive a message, this one is not receiving any message because this one is off, right? That's why it stays with the last value of the LEDs. Right? If you go into the source code, you can understand it. Tell me.
So the second mode is the same program?
Yeah, exactly the same. Yeah, exactly the same. Yeah, sorry for that. I have programmed these exactly with the same program so that they will basically broadcast on the same channel on the same AM ID, okay, so that they can communicate. Yes. No, everybody has both the transmission and the reception part. It depends on the application that you want to use, yeah, exactly. But a node can both transmit and receive, of course. Of course, not simultaneously, okay? So you can either transmit or receive, but you can do both things. Okay, now in the last 5 minutes, let's try to create a new simulation, okay? So you have to basically, first of all, compile the application for telosb. So go on TinyOS main apps, radio count to LEDs, and then type make telosb, so that you have the executable that you can run into Kuja. Now let's create a new simulation, removing the actual one. Now here we need also radio communication, right? And Kuja is nice because it will basically give you different radio medium to use, okay? Different models for radio communication. We will basically use the unit disk graph medium, where the signal which is received by a node is attenuated with respect to the distance between the transmitter and the receiver, okay? So I create a simulation, then I have to create again modes, so add modes, create new mode type, sky mode. I browse here and I go to TinyOS, main apps, radio count to LEDs, build, telos b main.x. Okay, I can create the modes. This time I will create two modes, okay, like here. Okay, I have these two modes here. I can also display, if you click with the right button, on mode tools, no, sorry, not here, on view, here in the network, you can display the radio environment, okay, the last item here, and it's, if you zoom out a little bit, let's see, come on, let me. Okay, so this is the coverage basically range for these two modes. Okay, the green part is where you can communicate, so the distance at which you can communicate. The gray part is where you start losing packets, and if you put these two nodes like this, you cannot communicate. Okay, in order to communicate, they both have to be in the green part. Okay, you see a 100%, which means 0% of packet loss, basically. Okay, so we can show the LEDs. Actually, there's another nice here in view. We can show the LEDs as rectangles here near the modes. Okay, I can again put the speed limits at 100% and start the simulation. See? They are blinking. Okay? So here you see the events that are basically occurring on the system. We will see this maybe better next time. What happens if I move a node away from the other? It's like basically turning off one of the two modes, okay? There's no reception of messages, so they will stop blinking, basically. And in fact, they stop, okay? If I move it again here, they start again blinking, right? No, in the gray area, we will see this when we look at contiguous simulation. You can specify what is the percentage of packet loss and this kind of stuff, okay? You can also modify what is the range of the green area and this kind of stuff, but we will see this later, okay? That's it. So this basically closes this lecture. We have seen the basics of TinyOS. Of course, it would be better if you play a little bit with TinyOS on your own. Okay, there are several examples already in there, so you can try to run that. You can read a little bit of documentation and this kind of stuff. Next time, we will see how to basically use the read interfaces, so how to read from sensors. We will see how to simulate with the other simulator, which is TOSSIM, which is a little bit more complicated. We will see, I guess, also how to interface this simulation with the Node-RED web application so that we can get measurements out from a wireless sensor network directly into the web, okay? So that, for example, you can put your measurements up to Cively or to a database or whatever you want. Okay, that's it. So